So today I just want to talk to you about the Perseverance mission, and I've worked most of the NASA robot mission, and usually I focus on the robotic arm. And here I'll give you an overview of what it's about, where we're going with Mars exploration, and to talk a little bit about the sampling and caching system for the robotic system. Okay, so Mars today, if you look at it, it looks very cold and deserted, and it looks like nothing useful can be found there. And but at the same time, we know that Mars is very close to Earth. It's within that sweet zone. So people are kind of curious as to why Mars is so different from Earth. And you know, we started looking at Mars for a while. I started in 2004 where we landed the Mars exploration rovers, and we had a theme, and the theme was on Earth. We know wherever there's water, there is life. So the theme was follow the water, go to Mars and see whether there's been water on Mars before or whether there's water on Mars at present. We did, and we did a lot of exploration. I worked on that mission, drove the rovers for over 5 years. And we were able to establish without any doubt that there's been water on Mars in the past. And they were not just pools of water, but oceans of water. And we don't know where they've gone. So we were able to establish that. The next one is that we send the Phoenix Mars lander, which I also work on, where we put the lander in the North Pole of Mars. And there we use a robotic arm to dig into the ice. Our satellites around Mars told us that 5 centimeters below the surface, there's going to be ice. And then we started digging, and 5 centimeters, we find the ice. We examine the ice, we look at the soil, and then we could detect that the soil is actually very similar to the soil on Earth that you plant. You can plant, your okra or your cassava or anything of that nature. So that also gives us some more information about the environment of Mars. Then we send the Curiosity rover, and the Curiosity rover's job was to find whether Mars is habitable. Are there conditions on Mars that will make it habitable? And we also Curiosity is still going, but we've been able to establish that Mars is a habitable environment that it could have sustained life in the past or probably in the future. Then this time around, we sent Curiosity that you also landed in a spectacular fashion, where the job is for us to go in there and identify rocks and materials that we would like to bring back to Earth. Because typically when we fly a rover, we cannot take all the instruments that we have, so typically we have very sophisticated instruments that fill large rooms. When you're taking them to Mars, you have to put it in the shoebox. So typically I have a shoebox in my office. When the scientists come and say, I want to fly this instrument, I just say, can you fit your instrument into this shoebox? So the scientists, by bringing samples back to Earth, we can do more sophisticated analysis and be able to determine the habitability of Mars or look for extant life or look for microbes. And that's the mission. The ultimate mission for Mars has always been bringing a sample back to Earth. So as I was saying, if you look at Mars today and the Mars several millions of years ago, you see that Mars had a lot of oceans, a lot of water, and it's changed. And we're very, very interested to understand what happens. The other thing is also on Earth, there's so much, activity, wind activity, flood and everything. So the records, the history has all been washed away, right? And all these tectonic events. So it's very difficult to find very ancient rocks. But if we go to Mars, we'll be able to find rocks that are very, very, very old. They're several billion years old. And the giga annum basically is referring to things in the billions. There are very few places on Earth where we find very old rocks that we can go and look into it and be able to look at the future, or at the past rather. I'll skip this. This basically tells you about how the various organisms kind of evolve.
Okay.
So one thing we know is that when we go out and we're looking for true rocks, we typically go and we can see fossils. We can see, they'll be about 600 million years old. Then We can also find what we call microbial biosignatures in rocks, right? And these are typically very, very old. And I'll show you a few of them. So going to Mars and trying to find rocks that have this type of signature is what we're looking for. So we can bring it back home and then we can do all the analysis. So the key is that we're looking for microbial biosignatures. We want to be able to capture these rocks and be able to kind of put them in test tubes and bring them back. So if you go to Shark Bay, these things exist on Earth, these stromatolites are actually organisms growing. They're very tiny organisms growing, and we can see them on Earth. We can see them in several places. And these are the type of signatures that we're looking for on Mars, if we'd be able to bring rocks with this type of signatures. Also, when you go to Australia, Western Australia, we find similar things in rocks of that nature. You can see this is a very small, you can see a pen. So we will be going on Mars, exploring and looking for rocks with this type of signatures, because we know if we can find something of that nature, we'll be able to tell about the biosignatures of things on Earth. So how are we going to bring rocks back to Earth? And to do that, we started with the Curiosity rover. We launched it and it did a spectacular landing. And we've started our sampling system, I think, in 2 weeks from now. And what it's going to do is it's going to explore. We landed in the crater, a delta, and then we're going to sample rocks, and then we're going to put them in test tubes and leave them on the surface of Mars. We're going to put them in different depots across Mars. Then in 26, but I think it's not going to be 2028, we're going to launch a series of missions to go and bring the samples back to Earth. To do that, we're going to work with the Europeans on that. The first thing we're going to do is we're going to launch what we call an Earth Return Orbiter, which is basically a satellite that is going to go around Mars. But this satellite is going to carry a NASA robotics system that is going to be able to capture a volleyball size. So like I said earlier on, we have samples that we've put in depots on Mars, and we're going to fetch them. When we fetch these samples, we're going to put them in a volleyball size container. And this volleyball size container, we're going to shoot it into Mars orbit. And this orbiter is going to interact with it and capture it. So this orbiter has got a NASA capture system, a robotic system. It will be around Mars for a while, providing there's some communication relay. And then within the same year, we're going to launch another mission that will have a lander and a rover from the Europeans and a robotic arm. This would land. When it lands, it releases the rover. The rover goes in and fetches all the tubes that we've left from Curiosity. It puts it in a volleyball-sized container. Then, it puts them in orbit. That will be the first rocket launch from another planet. It will put the volleyball-sized container into orbit. And then the previous spacecraft, the Earth Return Orbiter, which is already around Mars, will rendezvous, capture the volleyball-sized container with all the tubes in it, and then bring it very close to Earth, release it, and it will land somewhere in the Utah desert of the United States. We'll pick it up, and then we'll distribute it to scientists around the world. So when we talk about this is what it is. So Curiosity, as you saw, is one of many missions that is going to enable sample return from Mars to Earth. And this will make us be able to understand Mars better. It will also, once we get these samples, it will allow us to be able to prepare for humans to go to Mars. And we believe in the late 2030s, we will have humans on Mars to explore. And these are the mission objectives. We have a geology, we have an astrobiology, we have a sampling, and we're preparing for humans to land on Mars in the next few decades. So just to give you a sense, we have a lot of orbiters around Mars. I don't think most people have, like, you have satellites around here. And we even had more now that we have one from the UAE joining us. And then we have a couple of European ones, and we have a lot of rovers. The Europeans did not launch this rover in 2020. It's been postponed to 2022. But most of all this mission, apart from the Sojourner rover, I've worked on all these surface missions. And this is just to give you a sense of the different rovers that we've sent. In 1996, we sent the Sojourner Pathfinder. I didn't work on that one. Then we sent MER and Spirit. Then we sent Curiosity. And then we have Perseverance. So basically, you can think of Curiosity and Perseverance as like a Mini Cooper if you're in England, or I'm sure in Ghana we still have Coopers driving around. That's the size of the rover. And here I just want to give you a sense of where we're landing on Mars. So right now, we're what we call Jezero crater on Mars, and it's almost like the Volta Delta, right? So you have a delta where water is coming in and going out, and you can see, and most places on the Earth where we have deltas, we have a rich set of life, and that's exactly what we expect here. And you can see a typical delta. You have streams flowing in and out, and that's what Jezero looked like, and that's why we landed at Jezero, because it's most likely you might be able to get rocks and soil samples that might have a stunt life, past life. So I'm going to skip the launch. I think we've all seen the launch and the landings, and focus more on the so we had a spectacular landing that I think most of you have seen. What makes this landing very interesting is that this is the first time we actually had cameras watching all our deployments. Typically, we depend on telemetry to tell us that everything went well. So it was pretty exciting to see these things live, just to confirm how hardware functions. It was very cool. And also, in addition, when you're doing what we call entry, descent, landing, you cannot test it on Earth because you don't have the right gravity, you don't have the right atmosphere. We can test elements of it. So the first time you see it working is on Mars. So it's kind of scary at the same time, very exciting.
Nice.
I'll skip this. I think you've seen this ones. And one thing that I really enjoy is when we're able to coordinate our orbiters that are going around Mars to be able to take pictures of our spacecraft entering Mars. So here you can see that we see our spacecraft entering Mars and the parachute is out, and we're able to take pictures of it from orbiters around Mars. And that is a very cool engineering coordination. And this is when we landed, obviously, and you can see we landed very successfully. We see very good views. If you work on Mars for a while, you're not surprised to see all these outcrops. And the other thing we do is this is a prediction. We predict where we think all the stages that we will be deploying are going to land on Mars. So we get our orbiters to take the images after we landed to check our predict. So that means our trajectory predictions of where all this parachute, the back shell, the descent stage, the rover, and the heat shield are going to land. And it was all predict. So that was pretty cool to see. And then you can see the parachute clearly on the ground. And then you can see the rover. And when we landed, and then we have the flyaway of the sky crane, and it's going to crash into Mars. You see plumes of it feels like it is smoke, but it's not smoke. Actually, it's dust. And once we land, we take pictures of our vehicle. And I always, anytime I go across the continent, I like to. You can see here that's a sundial. The sundial is very special because our forefathers used sundial to tell direction and where the sun is.
Yeah.
And one of the things when I go across the continent, I like to remind kids is that space exploration is not very foreign to Africa. Actually, our forefathers walked the land from south to north, from west to east. And what they did is they look at the skies. And when they look at the skies, it was pretty wonderful, spectacular at that time. They didn't just admire it for the beauty of it. What they did is they mapped it. They put rocks, they put drawings to map the constellation. And they just didn't map it for the fun of it because they can draw. They actually use it to improve life on Earth. How did they do that? By creating calendars to know when to plant and when to harvest. and how to navigate from A to B. So our forefathers were at the forefront of space exploration. They were within the confines of Earth, but they were able to use the heavens to make life better on Earth. And humans have been doing that for millennia. And that's what space exploration is about. Space exploration is looking at the heavens and taking the things of the heavens to make life better on Earth. And that's why NASA is very special. Everything that we do, it helps everyone across the world. We are the only proper organization in the world that our technology touches everyone. Okay. Most people say, oh, why do you spend billions of dollars in space exploration? Because what it does is that it allows you to have your vaccination, right? Because you can go to very rural areas of this world, remote areas of this world. People can get vaccinated because of what? Coolers that we've been able to design, phase-changing materials that we use in space. It allows you to be able to keep these things cooler. You know, people take GPS for granted these days. People take the cell phone for granted these days. How did they come about? People, you know, it is satellite communication. So if you look at the developing world benefits greatly from space exploration, right? It opens the door for all this development that people have today. You know, people don't have potable water, but they have a smartphone. They can communicate. For today, somebody can load the whole Library of Congress on their smartphone. And this is what space exploration does. And it didn't start today. It started from prehistorical people walking the plains of Africa. And so these are some few rocks that when we landed, we took pictures of using. We have over 32 cameras on this vehicle to be able to take pictures and document where we are. So now you're getting to, once we land on the surface, that's where my team comes in. We drive the rovers and we do the exploration. And I'll just show you some of the cameras that we have on here. In addition, most of the missions that we run are international in nature. It's the US as a bulk of the instruments, but we have always contribution from Europe. Even on Curiosity, we have contribution from the Russians as well. And this is one area that, you know, we hope we can get African countries to also contribute payloads in the future. You can see we have France, Spain, Norway, and within the European countries, although France is the lead, there are other sub-countries involved. And here, although Spain is the lead, there will be other countries and Norway as well. So we have payloads from different nations. And here is showing you the ZCAM. It's a multispectral imaging system that has Zoom that we can get the videos. I'm sure if you've seen the videos of the helicopter flying, you see it comes from this camera. And it can take very high resolution images, actually hyperspectral images. And just to give you a sense of this instrument, typically these instruments, they are foil. You see gold wrappings around them, which is very good because it provides very good thermal, because Mars is very hot and very cold. So if you don't have a good thermal control, your measurements will be off, because your things will be expanding and contracting. So you need to be able to have a very fine thermal control. And then the next one is what we have engineering cameras on there. And basically we take those images to reconstruct the terrain, to know how to drive, and to be able to do better science with our instruments as well. And then here also you can see that we have what we call fiducials, these markers. Under these markers, we've done metrology on them. So we know exactly where they are, so we can take pictures of them and be able to calibrate our cameras to know what distance things are. And this is the robotic arm. And that's something I worked on with a whole lot of a team of people. We've got a drill. And this is the first time when we deployed it on Mars, and everything worked spectacular. We were kind of very pleased. The first deployment of the robotic arm. And then we have a lot of instrument. We have Pixel, which is an X-ray lithochemistry instrument. So, you know, if you remember your sciences, you know, we can take this instrument and we can look at a rock and we can tell the elementary composition of the rock. We can tell how much carbon is in it, how much calcium is in it, how much potassium. So it basically breaks the rock into different elements for you. And then we have the Sherlock, which is also a Raman, but what it does is it tells you the mineralogy of the rock. So you put this, you fire the X-ray against the rock, you can I could tell what minerals are in the rock. And then we have what we call the Watson. It's a high resolution microscopic image, so you can put it on and can see the structure of the rocks and the soil at the microscope level. And this is the first time that we turn our wheels on Mars. That's also very exciting to see that everything that you've engineered for over 6 years worked perfectly on Mars. And then we took our first drive, and as we're driving, we're taking images. And it's always exciting to send the first drive and see everything work. And then we have what we call, so as I said, we have this RIMFAX that's from Norway. It's a ground penetrating radar. So as we drive, we can look underneath the soil and tell what is underneath us. And then we have the MEDA, which is a wind instrument. So we can on Mars, as part of InSight, we can give you daily forecast within the region that we're on Mars that we've landed. We have a daily weather forecast that we provide on a daily basis. And, it's very exciting. Like we do on Earth, the satellites that we've developed over the years allowed us to predict weather very accurately. Is what you call the MOXIE. So the MOXIE takes in carbon dioxide and converts it into oxygen. This is very important because Mars is just carbon dioxide atmosphere, actually a very thin atmosphere. When we send humans to Mars, it's a very long trip. So it will be beneficial if you don't have to take so much with you, if you can make your own oxygen. And this is a very exciting payload, and we've been able to make a lot of oxygen on Mars since we've landed using MOXIE. So it gives us great confidence that in the next few decades we can send humans to Mars, and we don't have to take a lot of resources. We can take a manageable amount of resources, be able to generate oxygen on the surface of Mars. And then we have a technology demonstration, which is a helicopter. Mars has very thin atmosphere. To fly there, your dynamic pressure challenges are huge. And here also I worked on the rotor servo for this mission, and it's been very, very successful. Actually, we're very surprised. We wanted to test it for 90 seconds because we know for 90 seconds we can get the data that we need to be able to make modifications in the future. But we're still flying it, and it's been making some really spectacular long distance flights on Mars. This is the first thing to ever fly on another planet. And then here you can listen. I hope you can hear. So you can hear it flying. This was its fourth flight. And, you can hear what is going on Mars 100 million miles away. It's pretty exciting. You can see the helicopter take off, and it's spinning about 25 RPM, 25 revolutions per minute. You can see it go across and then across the surface. Very exciting. It's I don't think it's something we people predicted we're going to see in our lifetime. But
Nice.
Okay, so now the adventure begins. These are the kind of geological features that we're seeing, and now we're going to go in there and do the science. And to do the science, this is what we call the sampling caching system. So we have a robotic arm. You can think of it as how the human geologists work. The human geologist uses their hand and they use tools. So they go into their bag and they pick up different tools to use. They have a drill, they have a hammer. So we take a hand, which is a robotic arm that has 5 degrees of freedom. We put several tools at the wrist of it and effector, your fingers. So we have several tools on there. It's like a Swiss Army knife. It's got a drill, and the drill that it has drill bits. It can change them. It has places that he can store its samples. It has a carousel that rotates with the different bits, and it has a tube that it can store samples in it. And within the tube, it has something like what we call a test tube that you can put the samples in there, and it can cap the samples, and then it can store them. So on this mission, this is the first time on the robot we have two robotic arms, one on the outside and one on the inside of the rover. And I'll show you. And the goal here is to take the arm, unscrew the arm, after selecting the rock, put it on the rock, acquiring the sample, doing some science on the sample, storing the sample in the rover, sealing it, and then going to a depot and depositing the sample. Right, so I'll show you an animation, and we can look at a real. So you can see the drill. It's a very big drill. It's going to preload the drill, put a load on the drill to about 300 newtons. And the drill is going to, within the drill, there is a test tube, right? And then once it's drilled, the material is captured in the test tube like a core, like a round, think of it like some straight okra. And then it will come in, insert the tube into one of these carousels. And then it's the robot. I see there's a robotic arm inside that it's been passed. The big arm passes the tube to the smaller arm inside the rover. It goes in there, checks to make sure that it has enough material in the tube. When that check is done, it's going to measure how much, what is the volume of that. It's going to seal the tube. It's going to image it, and then it's going to put it in storage. And you're going to do this probably hundreds of times on Mars as we look at different samples. And then we store it and we drive around just like a geologist would do, walking across the plains or the savanna of Ghana. So, and then we also have two other payloads that we do what we call content science that we put on the rocks to be able to do the mineralogy, the elementary chemistry. On this mission, we're not doing wet chemistry. On Curiosity, we did wet chemistry where we have electrolytes, where we put the samples in to analyze. Okay, so I spend most of the time working on this system, what we call the sample caching system, to make sure that we can get it to work. So I'll talk a little bit about some of the tools that we have. So here, so the drill uses different tool bits, as you can see here, and these are all kind of gold plated here. These are the real flight system. This is the drill, and these are all the tools you can use regularly. You can think of it as sand, coring bit, breaking it to rock, abrading, cleaning the rock, and then launch abrading bit. This is what we put on before we launch. And then inside, the robotic arm inside, once it receives the tube, this is all the things that he can process, and this is where it stores them. And he's got about 43 tube storage locations that he can store them. And then he has to seal them, perform a lot of processes. So this is one of the most complicated robotic systems that we've ever launched. And then this is the actual hardware. You can see the robotic arm here, and this is all the stuff in there. It's a very impressive system to build, and to get it to work flawlessly is actually incredible. And here, hopefully this will work. I want to show you a little bit of we have a multidisciplinary team that works this from both generational, geography, and race as well. If I can get this thing to work. I'll try again. Let me get out of this mode and see. There you go.
That's it.
So this is in the clean room. This is the flight rover. We're playing with the robotic arm, testing it, and this is in the test bed.
Robots that go into space. The sampling and caching system on the Mars 2020 mission is the most complicated, most sophisticated thing that we know how to build. This is the system that allows us to take core samples of rocky material on the surface of Mars, carefully seal them in very sterile, clean vessels for eventual return to Earth. We've been working on this sampling and caching system for 7 years, and that's because it's a tough job.
We're testing the equipment to make sure that it's going to work when we get to Mars. It has to function on its own. We have to think of all eventual possibilities and try them here first. And then if they don't work, change it now, because we can't make any changes later.
To drill into the rock on Mars, pull out intact core samples, seal them hermetically, and to be all done autonomously by a robot hanging off the end of a rover on the surface of Mars has been a challenge. We've got actually 3 robots necessary to do the sample and caching system. Our big robotic arm out on the front of the rover, that takes our drill, pushes it against the surface, and allows us to take core samples. Then we put that core sample in the bit carousel, the second robot that takes that from the robot arm and puts it down inside our adaptive caching system. This is the part of the sample and caching system inside the rover. We've got a little tiny robot, a special robot arm called the SHAW, the sample handling arm. It takes the samples out of the bit carousel and moves them through volume assessment, image taking, and eventually to sealing, and then replaces the cylinder containing the sample in a storage spot, all on its own in the matter of a few hours. We have designs on bringing them back in a decade. Mars has been at the fore of our consciousness about the questions of life. Could life exist in one of our nearest neighbors? I think we have a lot to learn, life or no life, about the evolution of our solar system, about our planet, by looking in depth at rocks brought back from Mars.
Okay.
Yeah.
I think I have to get out of the view that I'm in now. I don't know, change view. Can you guys see the whole screen?
Yes, I can.
Okay, so once we get the samples, we're going to put the samples, like I said, in depots. We drop the samples, and then we can. So the samples are dropped on the surface of Mars. Then in a few years, we launch a lander with a rover on top of it. It'll go in, pick up all the samples, bring it back to the lander. Inside the lander, we have what we call the Mars Ascent Vehicle. That will be the first rocket to ever be launched from another planet. And that's also preparing us for human landing and return from Mars as well. So we put the volleyball-sized container with all the tubes in it. We launch it to the orbit of Mars. Once we get into the orbit, we release it. It can be in the orbit of Mars for several decades, right? Just in case when we try to capture it the first time, we're not successful, it will be in orbit for a long time. We have our Earth return orbiter with the Mars robotic system and the ESA spacecraft, rendezvous with it, capture it. Then it's returned to Earth and it drops in the Utah desert. We pick it up, and then we distribute it to scientists around the world so that we can do the science and be able to look at rocks from Mars and be able to assess understand how our planets evolve and look at our solar system. In JPL, one of our mottos is we dare mighty things. We don't do things that are simple. We do things that are hard. And because we know humans are capable of doing very difficult and challenging things, and we want to stretch ourselves.
Yeah.
Okay, so that's all I have. So the presentation was just that, and then we want to have more interaction. I think that's what Ray wanted, so that people can go back and forth. And I like to encourage people that there are no wrong questions. The only bad question is the question you don't ask.
Yes. Oh, thank you so much. Let me see. How can I unmute? Okay. Now you can unmute yourselves. Yeah. Thank you. This is fascinating stuff. Before I go on, let me just Let me just make an announcement next. So we do this presentation once a month. We try to do it at the end of the month if time allows us. Next month, which is August, on the 28th, we have Jan Samuel Hansen, who will be talking on the topic of mental health. It's also very, very important. So yeah, try and join us next next 28th. Okay, I'm gonna try and go according to the list, but I have one question though. So in all these this exploration, this robotics, Dr. Ollenu, what really tickles you? Is it the trying to find life on Mars, or is just about your robotic arm and it working, and it's what really it kind of tickles you?
So I think my fascination with things is not necessarily whether it's Mars or anything. It's just solving problems, and I just think that's one thing that GSTS does well. That we go to the workshops and we solve problems. So to me, if we don't have any problems, we don't need engineers. You don't need GSTS if you don't have a problem. So when I wake up every day, I thank God for problems, because that's why we have engineers to solve problems. We have medical doctors to solve problems. So it's about solving a problem and being trained to solve a problem, to think systematically through the problem and be able to do the analysis to come up with a solution. Even if you cannot find a solution, you still learn.
Yeah.
So it's about learning and solving problems.
Yeah. Good. Now there's somebody said we had Sandal in primary and middle schools. Okay. And there's another question. Says, Doc, I attended a lecture by Department Director of Astrophysics Lab in Cransford University here in the UK on cleaning up the junk in space. Is there a danger of doing a similar thing around Mars?
Yes, I think, that's why I say it's about solving problems. If we have a junk problem, it creates an engineering solution. It creates people start thinking about it. But I think Mars is managed very carefully so that we don't have junk all over the place, right? We know we're going to send humans to Mars. The planet, we have what we call planetary protection, where there's international agreement that you don't pollute the planets. You don't send especially life from Earth to Mars. So like most of our spacecraft are baked just very high temperatures so that we make sure we don't send our own lives to Mars. But there's a consciousness there that we don't, you don't want to make it a dumping ground. At the same time, we want to explore. So there's a fine balance. The space junk that people are talking about, yes, is real, but it actually offers opportunity for new technologies to be developed to manage. Because humans, like I've said, from our forefathers, we've always used the heavens to make life better on Earth. And we're not going to stop. That's the human endeavor. But what we also have to do is to be responsible. And I know there are several technologies being worked to be able to clean low Earth orbit of all this satellite debris. So I think it's an opportunity rather than something that is a distraction. Yeah.
Okay. Dr. Kwa has got his hands up.
Yeah, Doc, as a follow-up, how did we allow somebody must have recognized the fact that the junk was building up around the Earth's orbit? How did we manage to let it get so bad? Because what I saw on this lecture was really frightening. Yes, some people have begun developing various ways for cleaning it, but how did we get to that point where it got so bad?
So I don't know whether, when these things are painted, actually space is very large.
Yes.
So when people say things are close by, they're close by in the areas of their interest. But I don't think it's not healthy, but I don't think it's as bad as it's presented. But you also have to understand that to get communication working, People were more driven by solving problems. There were urgent problems on Earth to be able to watch TV across the world, to be able to communicate.
Yes.
So in terms of making those progresses, that was a low priority. People want to launch as many satellites as they could just to be able to keep up with communication. And then everything, the economy will fall apart, right?
Yeah.
Without those launches and all the satellites, you wouldn't have the economy that you have today. So that was the main emphasis. But now that you have a stable economy, now you're going to think about, oh, what other problems have we created? Right? It's just like mining. People, you mine gold for a long time. Nobody thought about the environmental, because it was people needed the cash to build the country. So I think it's a chicken and egg problem. It's one of those things but I tend to see, I don't typically see problems. I see opportunity. And I think when I talk to students, I always say, when somebody's problem is your opportunity, you want to take advantage of that.
Good.
Thank you.
Okay.
So one thing, at the same thing, people say, oh, you're going to space, but we don't have water to drink. And I always have to remind them, there's enough water on Earth. Look at the ocean.
Yes.
What we lack is technology.
Yes.
If every problem you see, there's resource to fix it, what you lack is technology. If you can focus on developing technology to solve problems. Okay.
So in the 80s, when we were leaving school, Form 5 especially, people will be writing their names on or inscribing their names on the wall, said, "Oh, I was here some," kind of. Is there any part of you that kind of said, let me write or inscribe something on this this robot whilst it's going out in Mars, so that if there's some extraterrestrial life out there, they'll have your name saying, yeah, you were there some.
Yeah, so I think when I was at GSTS, I was against that kind of graffiti kind of stuff.
Okay.
I don't think I have my name anywhere. I was one of those purists,
Oh, good.
Yeah. But on our spacecraft, every spacecraft, we do allow people to put their names on the disk. So every spacecraft that I work on is a disk. It's open to the public. And I think giving people from all over the world send their names in, and we put it on a disk. So that's how we get our names onto it, yeah.
Okay.
Well, we don't graffiti the spacecraft.
You don't. Okay. Anybody wants to ask a question out there?
Tata.
Yes. Tata. Okay.
Okay.
Yeah, Tata.
Hi, Doc. Good. That's a very nice one. We are very pleased to hear from you. Just want to ask a question. What is your plan apart from the school, robotics? Have you got any big plan in terms of helping our country? Yeah. Any links or lectures for them to gain from this wonderful knowledge you've just exposed? Yeah.
Okay, thanks for the question. So I think I do a lot more in Ghana and Africa than most people think. So I think, opening the doors so most of the foundational work we do is the passion to connect science theory to practice. One thing that I found that GSTS was fairly good at it was able to connect, the Tinker drawing to fabricating stuff, or that connection always existed. But what was lacking in general was, somebody goes into class, they learn the reflection, the refraction of light, and it's just basic theory. And it's very difficult for the kid to know what uses it, right? So for example, we have a program led by Dr. Yao Okrikwirichi and other old boy of us, where we call, as part of the foundation, what we call the Robotics Inspired Science Education. And the key thing is robotics inspired science education. Robotics is to draw the kids in. Because when I tell a kid, oh, let's go do science, because of the culture, they see science as very foreign. But I say, go build a robot, they want to come and build a robot. But in building the robot, we're applying all the principles that you learn in school. For example, we usually do line following. So you have a black line on a white mat, you're going to follow. And to do that, we take all the principles that they've learned in school, reflection and reflection of light. So when light reflects on the white surface, you get more back, right? On the black surface, it absorbs it. The kid learns this in class, but the teacher just goes and just tells it. But here, they're able to put it in application, and they understand. And what we realized, and I was very passionate, so most of the kids that take our program, when they go back to school, they do better in science because they're able to see that all the theories that they've been taught in class is actually applicable in solving real world problems. And in addition, science is not foreign to Africa, right? So when you go to school, the textbooks we use and everything enforces that science is something that is foreign. But science is what you do every day. So like, especially when we have girls, I go in and say, look, you are the best chemist if you cook. Cooking is a very complicated chemistry project. Okay. And to me, that is the connection that I want to make. So I think I'm very passionate about that. I think we've made a lot of impact. You know, we have a lot of kids, I think a handful of kids that have got scholarship because of our program. And we have one guy just finish Berkeley. And then we have a few girls that have gone through the program that have made impact. So I think I'm a firm believer, bottoms up is what changes the country, not top down. Yeah. So talking to the youth, I do a lot of youth programs. I do a lot of presentation in the country and across the continent as well. So I think I'm very comfortable with my contribution to the nation. And I'm also a fellow of the Academy of Sciences there. And I'm also on the presidential technology advisory committee or something of that nature as well. So
thanks so much. That is really great to hear. That is the difference we saw when we came here. It's about experiential learning. If we don't apply it, it never works. Thanks so much. Yeah.
Okay. Thank you.
Giant Odami. Yeah, Giant Odami Adams.
Yeah. Yes, sir.
Yeah.
Thank you so much, Dr. Enu. Great presentation. I have a couple of questions. I think that's just to piggyback on the previous question that you just answered. I know a lot of countries have contributed to this program. How can Ghana position itself to contribute to this and also to benefit from this? What are the problems that you are seeing being involved with, Ghana in the situation that we are in right now? And my second question is, I know a lot of consideration was taken in place before this launch. What did you wish you would have included in this particular mission that you just accomplished? And that's all I have.
Yes, so, I think you got to think of a nation as very differently, that a nation is there to build a certain ecosystem, and for that ecosystem to be able to flourish generation after generation, right? So I think if you frame the question that way, then the Ghana problem, you can solve the problem. But if you look at it as a short term, how do we feed people today? Then you get into this cycle. So we're in a cycle where it's almost a survival cycle rather than existential, right? Saying, how do we create a society that is sustainable, that will survive? To do that, you need leaders to be able to look at what the future holds. Right now, I like to call myself a futurist. We know what the future is going to look like. The future is what? Technology, right? So that means, what do? You focus your educational system on that path, right?
Yep.
You know that these days we're using fewer and fewer resources to build more and more. So if I'm mining, I can mine as much. I'm not going to get a lot of money for it, right? So I think that is what I believe. It's, it's not because the politicians are bad or anything, but it's because they have not been educated to think in that sense, right? So when I did my lecture for the fellow of the academy, I told them, we don't need spiritualists. We need futurists, right? And in the country, or most of African countries, except for Rwanda, when you go, you land at the airport and then you start moving, all the signboards tells you about spiritualists, right? Okay, and I'm going to digress a little bit. So I asked the professors that I put in the room, if the president of Ghana has 2 visitors in his office, they're waiting, and the secretary goes and say, I have a professor here who has an advice for you, and I have a spiritualist here that has a prophecy for you. Who is the president going to let in first?
Most likely the spiritualist.
The spiritualist.
and people thought it was funny, and some people were upset. But it kind of tells you the mindset, right? And my mindset is, we need to change the name of the education department to the Department of the Future. Because when you do that, it changes the mindset for the people working there. You're not working for today, you're working for what? The future. So everything you do plan, you're planning with the future in mind, right? And people think it's so minor, but it's very important that people know that whatever we're doing for the future rather than the now. And I think that's something that probably the United States, we have decadal service. For example, the work that we do today was planned 20 years ago. So we have a planetary decadal survey that tells us what people should be thinking of the next 10 years, the next 20 years. And that's why, you see all these wonderful things. And I've tried to do that in Ghana. Say, let's talk to people. Let's start thinking about planning for the future, right? So that you can have a roadmap leading to the future. But I think there's a great opportunity. I've been very privileged to travel across the country all the way to the north. One of the best experience I had was like 11 years ago, where I convinced the Department of State here for us to start this program, and we went to Tamale, and then we had all students from all over the northern region. And the embassy was very worried because I said I was going to teach these kids robotics, and I'm going to teach them within 2 days, they'll be able to program a robot to do some really clever stuff. And they said, but these people haven't used a computer before. I said, precisely why I wanted to show you that they are capable and they're going to program. By the end of the day, kids that have only seen chalkboard computer say, this is a keyboard, they never programmed before they were programming. And my friends were fascinated. How could they program? I said, everybody in Ghana is a great programmer. Why? Because they can tell you directions. And people don't understand what the fundamentals of programming is telling directions. So if I have somebody from Wa, they don't have a street address, but they can tell me that walk here, you see this guy selling Gary here. When you get there, take a left turn. You see this guy selling, there's a lottery box here. The kids in Africa are great programmers because that's the fundamental of programming. When you're trying to teach somebody programming, you don't go and say, let me teach you structure. You say program is about telling directions. You teach them from what they already know. So these kids were able to take it and say, look, I'm just telling the robot directions. From here, I'm trying to tell them to go by to that chop bar over there. How do I direct people to that chop bar? And they were fast because I know that, because I understand the culture. And I've just tried. There's so much potential. It's a matter of us being able to do things from the bottom up, being able to extract this potential from our kids. So I don't worry too much about the youth or anything. I worry more about the leadership. How do we educate people to be able to get the most of our kids? In terms of the question about the mission, we're very constrained in terms of, we are using a computer that is like from the 70s because of radiation. So we don't have a lot of capabilities. So most of the things that we put on are we had to put a baseline in, but we wanted to put more advanced software. So we're working on more advanced software to upload to the spacecraft to be able to do things more autonomously to get a lot more out of it. So that answers that part of the question. I hope I answered your first question. In Ghana, I think there's so much potential. It's a matter of trying to refocus leadership from seeing problems to seeing opportunities. And to me, that's what has changed my life, that I don't see problems. I get really mad when people say there's not enough water. I say, no, there's not enough technology, because there's a lot of ocean out there. If I have good technology, I can provide you drinking water.
Yeah. Well done. Thank you so much. President Jan Dabekwe, you have got a question?
Yeah, thank you, Dr. Ollenu, for the talk. It was very interesting. I have so one question biology and one question advising. So far, we found water on Mars. Have you guys found any biomolecules like amino acids, agents? Even if you've not found an organism, have you found any biomolecules yet?
So there are organic signatures that have been detected, but probably not in sufficient amount to make any assertions. But from this mission, we will be able to refine those models and be able to make more definitive assertions on that. Yeah. Okay.
So that's one. The other one is, if you are advising a young student who wants to get into robotics or aeronautics, any of those things, what would be your advice, especially someone coming from Ghana? I've heard advice like do mechanical engineering and then specialize. I've had people come to me saying that they want to do aeronautic engineering. You being in the field, what is your advice with regards to that?
So this is a very interesting question, because it's not a question that only exists in Ghana, it exists here as well. I get thousands of kids and parents that I have to talk to. So robotics is a multidisciplinary field. You can approach it these days. I think a few schools have started robotics undergraduate program, but usually it's a graduate program. So most people come to robotics from several areas. They come in from aeronautics, mechanical, computer science, software engineering, mechanical engineering. So people coming from different fields, and then they go do their master's. So when they come in, they're a little bit skewed in one way or the other. The best folks that do very well in robotics are people that do a lot of projects. Okay, so the people that robotics is an experimental science. Actually, it's a very frustrating one, because you build stuff, they don't always work, and you have to you have to persevere. So I think it depends on, for somebody from Ghana, I think if I don't know a lot about the aeronautic engineering and tech, but if the aeronautic engineering and tech is very system engineering based, that means they'll come, if they do that, then they come into robotics, they'll come to robotics from a system engineering aspect of it. But I think if you come in from a mechanical with a little bit of electronics background from somebody like Ghana, that means you can build stuff, you do a lot of electronics, a little bit of software, you'll be better off, because then you have the hands-on experience. Usually people that do aeronautics coming from a system and they haven't done programming. But I advise a few people like Georgia Tech and other places where we encourage them to do their aeronautics, do software engineering, and do a little bit of mechanical engineering. So when they come in, they have that cross-cutting skills. So the emphasis is on cross-cutting skills, not just a field. It's very difficult to come in, I'm just a software engineer. You need to know about something about sensing. You need to know a little bit about the mechanical, the actuation, so that you can be able to do stuff. Unless you just want to specialize in artificial intelligence, then the software and the algorithmic part is very helpful. So I hope that helps answer your question.
Yeah, thank you.
So Emmanuel Kofi. Yeah, Emmanuel, unmute.
He's muted.
Unmute.
Sorry, good afternoon. This is Emmanuel Kofi.
Mabo,
alias
okay.
Mabo. Thanks so much. That's my house P doing the show, doing the honors. And my president, good afternoon as well. Abekwe. Actually, I didn't know of the program. I saw the program and I just joined in. I didn't hear the first aspect of it, but I heard House P mention about seeing a problem means an opportunity. Our country here in Ghana, it's problem here, problem there. And I have had my feeling all along that we have lots of opportunities seeing our problems. And I'm happy he mentioned it. I believe that the robotics is one of the ways that we can take opportunity, we can take advantage of to help solve the problems of Ghana. But I hope that we can also look at our other avenues, if we have any, or our own team of giants, if we have any, to start thinking of opportunities. We've seen our country as a country of opportunities, because we don't only have to be mentioning problems that we have in Ghana here, but to identify those problems that we have and then turn our heads around into heads of opportunity, areas of opportunities, and take advantage to see how best we can help.
Thank you very much, Senior Mabo.
Thanks so much.
Okay.
Sure, thanks. Is that a papu?
Yes.
Thanks.
Giant Vanderpoy. The last one, make it a good one, please. Can you unmute?
He's muted.
Can you unmute, Vampi?
Yeah, thank you very much. Brilliant talk. I really enjoyed it. So my question is, considering the size of the rover, there must have been, some energy demand. So I'm wondering, I think the obvious one is maybe solar stroke batteries, but is this technology the same as we have here, or maybe the one that they are using there is more advanced? So I was just wondering, I think he mentioned that it was about the size of a Mini Cooper or something, which means that it's a very sizable machine. So I was just wondering the kind of energy demands and how they meet that. The other one is a personal one about, how, Dr. Ollenu, how did you feel, with a successful landing and everything, and this kind of weight on your mind? If it was me, I would definitely have some sleepless nights, and not to talk about, for the first deployment or, whatever, to make sure that your arm was working, or even from what you are saying is a lot more than just the arm, because you mentioned being involved in the first helicopter flight as well. So how was the feeling before some of these things went online, and then with the success of it, how did you feel about that? Thank you.
Okay. So in terms of power, space exploration has actually advanced solar technology. So here we use what we call RTG. That's a radio isotope thermal generator. So the source is a is a nuclear material, and you take the heat that is generated from the nuclear material to generate power. So we have this RTG at the back it's going to outlast the rover because of its half-life. And it's going to basically generate about 120 watts of power. And we're using it to run a very complicated laboratory. And then you have a battery. So the RTG charges the battery and you run off the battery. And the battery is a lithium-ion battery as well. And space technology is also advanced battery technology. Actually, when I do lectures in Ghana, when I talk about this, and I talk to high school and junior school students, I try to use this to teach nuclear physics and chemistry, because this is an example. When I was in school, people just talk about it, but you don't even understand how to use it in real life, and the students can connect to it. So that's how we power it. In terms of the how one feels about the success and the challenges, I think we work in a very high risk in terms of that risk field. So we expect failures, so you're comfortable with failures. And I think that's one aspect of education that I'm very passionate about, that if you're getting A's all the time, you're actually not doing well. That means you're working in your comfort zone, you're not stretching yourself. So the emphasis is, everybody should get A+. If you're getting A+, that means the work is too easy for you. You should be stretching yourself, and that's what we do at JPL. We do things that we know are going to fail. Some of them will fail. You want to stretch yourself because you deal with the unknown. And I think getting kids to do robotics and for them to deal with the unknown because they plan the robot for something and then we change the course, it's something that I think getting kids more comfortable with would go a long way to provide kids that are very strong in their field and always expect a challenge, because life is a challenge. I don't think you wake up one day and think you figured everything out. There's always uncertainty. And I think learning to deal with uncertainty is something that we've done here, that, sometimes you worry a little bit, but you don't worry as much as if you want everything to be perfect. We expect we're going to get some failures on us. Everything worked. Sometimes they don't work. We have to send a fix. We have to figure it. So you're always there and saying, you're planning, what am I going to do? We always have a workaround. There's always a plan A, plan B, plan C, plan D, right? And that's something that when I talk to kids again, I say, look, you always have to have multiple plans. Things do go wrong, and it's going to go wrong. Just when it goes wrong, don't be surprised. Have a plan. So that's what gives us comfort, that we have a plan. And even if the plan doesn't work, we know we can plan again. It's not the end of the world. Yep. People will make fun of you in the media and other things, but that's life. You just have to roll the punches, but know that you did your best. You can do more than your best.
Thank you so much. Can I just say that, yeah, I'm really grateful for you to, having answered the call from LinkedIn, and conversation started from there. And then you were so happy, although you are very, very busy. I realized that, to come and give us a talk. I was trying to get the link to the school as well, so that students could kind of listen to this talk, but I realized that it would have been a lot of hurdles to get through. We can't just speak to students directly without the appropriate kind of permissions and stuff. So, but it's something that we'll probably try and fix, so that in another time you can speak to the students directly, or anytime you're in Ghana. Maybe you've done it already. You can also.
I think I was there in 2011. So we had our first robotics system at GSTS. Yes.
Okay, because that's something we are trying to revive. Our robotics kind of team in GSTS. So people are quite keen because it gives us some gravitas out there, and you being kind of a flag bearer, a giant out there, we always pointing our finger at you. So, but thank you so much for today. It's been amazing, and I hope that when we call on you again, you would respond like you did.
Yes, I would say thanks a lot. I learned a lot talking to all of you, and I wish you the best. I think we have a great country, there are great opportunities, and with everybody's help, we'll have a sustainable development.
Yeah, thanks. But anyway, you can hold on. We can have a chat. Oh, Geoffrey, another friend of mine, but you came late. Sorry.
Okay, so I can give you another 14 minutes.
Oh, that's good.
If you want to have,
that's good, Jeff.
People have made time to come to talk. I just think we have to respect all of their time.
All right, Jeff, fire away.
All right, Ray.
No, Jeff first. Sorry, Jeff.
Oh,
first.
Jeff.
Yeah, hello, Dr. Ollenu. I just want to see how I can get in touch with you one-on-one, and if it's possible. This is Pichu.
I'll put my email in the chat. You can send me Gmail.
All right. Okay. Thank you.
There's no guarantee that it will be responded in a timely manner.
Okay. All right. Okay. Thanks. Yeah.
Okay. Abekwe.
Yeah. I was just going to talk about something that Dr. Ollenu said about the kind of training that we had at GSTS, the project-based training, which seems to be one of the things that is missing. And I hope that we can reinstall or reestablish it again, because like he's saying, it's so important, not only in engineering, but I think with almost every aspect of work life, right? Having something and doing it, that connection. I tell people that maybe it's now common in Ghana, but at GSTS, we had project-based learning before it became a popular thing that people are talking about now, and I hope that we can.
Yeah, I remember making a candlestick for my metal work assignment, and I had to build a stool for my woodwork. I didn't like woodwork too much, but it was dusty. But yeah, but one thing I was really disappointed when I went to GSTS, and I think it's something that I was very passionate about, is people not treating school property with respect.
Yes.
Okay. Yes. And that I feel very passionate. When I was GSTS, I couldn't understand why people did that. And if you look at the school and you look at the broken windows and the dormitories and everything, it's because people don't treat, and I don't know how we build a culture within the school where when people come to the school, they feel ownership of the school. So they don't want to destroy it. They feel it is their home. It's not something foreign, right? And I think, to me, if we can, I think to me, that's one thing I learned as a kid, that you treat everybody's things with respect. And when you go to work, and that's where, you can look at some of the problems we have in the country. People go to work, they don't have ownership of the work. And I think if we can start that culture at GSTS, it'll be very helpful. When kids get out of school, they look at the bed they're sleeping in, they don't say, I can break it, it's not this government thing. If we see that culture at GSTS, I think it will be very helpful, because I took the U.S. ambassador has never been. I took him there. It was very embarrassing and very scary, because the way the place has been, I don't think it's a maintenance issue per se. There's some maintenance challenges, but all the windows and other things being broken, it's not a maintenance thing. It's not decaying or anything. It's just people don't have that ownership. So that's one thing I would say we need to work on.
Thank you.
Is Jeff Sands up again, or is it the previous one? Jeff.
Oh, I think it's the previous one. Oh, so it's the previous one. Yeah. Okay. Sorry about that. Yeah.
That's fine. William, did you want to say something again?
Yeah. Yes, I do. Yeah. So I was wondering, Dr. Ollenu, please, what is in terms of the geographical placement of the previous rovers and the Curiosity? I'm just wondering, the kind of dispersion you have in terms of maybe your sample collection and everything, because I realized that you were talking about getting the samples back to Earth for analysis, but you do have a whole lot of data, I suppose, considering the fact that you have these imaging cameras that can take, chemical analysis just by, analyzing these cores and things that you have. So even without, God forbid, but if anything goes wrong, I think you have still a lot of data to work on already with what you have. How dispersed are the rovers, and how much information in terms of contribution, how much science have the other ones done? If looking at the Curiosity alone, the amount of data that you're acquiring so far, I was just wondering about that.
So maybe you're talking about geographical dispersion. The rovers, they cannot drive to each other's location. They're regionally very different. So in Mars, we landed mostly in the south, because the north is very high mountains, and you don't have enough time to slow down before you get to the surface. But in terms of geographical diversity of the data that we have, it's very good. But we don't have the resolution with the payloads or the science instruments that we have to be able to do certain analysis. That's why you need a sample to come to Earth, so you can do more comprehensive analysis.
Yeah. Okay, thank you.
It looks as if you're running out of questions, so
yeah.
Anytime you run out, we can just call it quits.
Otherwise,
I just have one question here.
Okay.
Can Can I ask one question?
Yeah, go on.
Okay, thank you. Dr. Ollenu, I'm glad you mentioned the iteration of infrastructure at GSTS. And I just want to ask a question, probably another aspect of it in terms of education, quality of education. Because as an association, I just want your, I would say, your input on your advice for the association. A lot of our focus has been as providing or improving the infrastructure of the school. What will be your advice, let's say, if we want to improve on the quality of education for the school also in that region?
Yeah, so I get a lot of email from the American Association. I do contribute to it. I think, to me, it starts with the people that go, the students that go to GSTS. Trying to, I don't want to use indoctrination, trying to make, when I went to GSTS, we're the best in West Africa. As a tanker education, we had people from Liberia, people coming from all over Africa to come in. So you had that pride. When you went there, they told you, I think Cujo was the headmaster a long time ago when I joined, before he left, but instilled that pride in the students that you had at the when I went there, I didn't get the sense that the kids had the same thing, that we are one of the premium educational system in all of West Africa or Africa. So trying to get that, and then people have to feel that they should feel privileged to be in the school. So I try to start with the students, and then they are responsible to preserve things for the next generation. So I think that's where I'll start. And then the other emphasis that maybe we need to change probably as a nation is the emphasis should not be on, you're there just to pass your exams and leave, right? So when you're training people to pass tests, it's a completely different mindset. Yeah. But if you're training people to problem solvers, which GSTS is, because when I went there, the woodwork, the metalwork, and the drawings that we learn, you're there to solve a problem. And I think even if it's not project-based, people knowing that everything we're learning is to solve a problem, because in this world, there are going to be problems. And we're there to look at problems in our society, bring them in, and see how we can. So I think it's more of a mindset, and the teachers, because you have teachers there that are teaching people to pass tests. They're not teaching people to solve problems. And as a technical school, all we should be doing is go to MIT, go to all the big schools, all the best schools in the world. They are not teaching the kids to pass tests, to solve problems. Go to Stanford, it's kind of amazing. Problems. You're learning to solve problems, and that kind of mentality. So I'm not a big fan of saying, let's buy books for the library. It's important, but if we can have a more education that focuses the people, prepare them for that kind of, I think, to me, having seminars with kids so that when they come in, it's a different mindset. I think will produce probably really excellent students that would, although we'll do even better now. Yeah.
Cool. Thank you so much.
Well, if there is no question, let me ask Doc one question. Doc, was Oslo your house prefect?
Can you say that again?
Was Oslo Frank your house prefect then?
I can't remember the name.
Yeah. So he was in your house, isn't it?
No, he was in house 7.
I was in Ritchie Hall.
Oh, you were in Ritchie 4?
Yes, house 1.
Yeah.
Yes.
Okay.
No, Ritchie is not 4. Ritchie is 1.
I was in house 1, yes.
Ritchie 1. Yeah, Oslo was in 1, I guess. Was it?
I thought it was in 7.
Okay, right.
Oslo was in 1, but I
1. Oslo was in 1. Yeah, I know.
I left in 73.
Yeah.
I left since form in 72.
Okay.
Yeah.
Good.
I was way before my time. I got a GST, I think 1978 or something like that. Yeah.
Yeah. Okay. So you were with Osewusu, yeah.
Oh, thank you so much. Yeah, when we start talking about 78, 71 and all that, you know, then
then it's time to close.
They were interesting times.
Then you know the next one is we were having ice cream and you know, then you know that it's time to close. Yes. So, thank you very much. But you can stay on, especially UK guys. You can stay on. We can have a chat.
Okay. God bless. Thanks,
thank
guys.
you so
Keep
much.
in touch.
Thank you
Okay.
so much.
Bye.
Yeah.
Bye. Bye.
God bless. Bye-bye.